founder and CEO of Bloq Quantum. So you must be wondering, this is a Gen AI conference. Why are we talking about quantum computing, right? I think you should ask organizers that question. When they also asked me to take a session, I was also surprised. But nonetheless, here I am. Um, but I'll give a small cautionary note before. Quantum computing is a very, very vast space. Woman, it's a very vast space. And each of the session that, each of the slide that I'll be giving here, that itself can take 1 hour session separately. So I've packed a lot of data, a lot of information. So please forgive me for that. Try to click photos whenever you can so that you'll be able to go back and search more on it. Think of it as a base fundamental building block for you to get more information. So on that note, I'll start. Oh, okay. Oh, there it is. So first, who am I, right? Who is this guy? He barely seems like he would have graduated college. Who is he to lecture us on quantum computing? But yeah, nonetheless, so I've done MS in physics from Azure Pune. I did quantum computing, quantum research, but then I found out, okay, this is not my area. Research is not my area. Then I went on to work at 2 startups. One was in India, one was in Canada. Both of them remote work. And then I co-founded my own company called Bloq Quantum. So we have raised a pre-seed round of 1.3 CR from Inflection Point Ventures, and we have finally completed our product development. So I'll be happy to show you the product as well, what we are building. So jumping to what is quantum computing. Before going to that, what comes to your mind when you hear quantum computing? You would have heard a very, very basic idea. You would have heard somewhere, okay, quantum computing, quantum computing. What comes to your mind when you hear quantum computing? What comes to your mind? Nothing? No. Haven't anybody heard about quantum computing? Yeah, quantum physics you would have heard. Like, what comes to your mind when you hear quantum computing? Nothing, okay. Yeah, yeah, atoms, because it tries to use atoms to you make a computer. Yeah. Any? Yes. Yes. So you like some of you have a very basic idea. So I'll try to get all those fundamentals about quantum computing. So the talk is about quantum algorithms and software. So first we need to cover about quantum computing, then comes to algorithm, then comes to software. So quantum computing uses qubits instead of bits. So qubits are essentially fundamental building block of our nature. So it can be atoms, it can be ions, it can be electrons, it can be photons. So basically whatever we can't touch. So we use that to build a quantum computer. So it's a very fascinating field how to build a quantum computer in itself. The second thing is it's exponentially faster. So that there is theoretical backing saying it is exponentially faster. Now, the third thing will be it'll be computationally cheaper as well. So right now we use big data center of GPUs to train our ML models. But once quantum computer comes in, you'll be able to train these models with very less amount of compute power, because a quantum computer with less number of qubit can actually do the same amount of work that, let's say, a GPU, the best high-end GPU can't even do. And the fourth point about quantum computing is that it helps us to solve some of the hardest problems in humanity, starting from finance to healthcare. So there are plethora of use cases, plethora of problem statement that is currently unsolvable because of a fundamental reason that this problem statement is not suitable for the current computers. They are the computers that are built using bits, that is the voltages, ones and zeros. They won't be able to scale towards the complexity of the data set, complexity of the problem. So I'll give an example in the next slide to show what is that sort of problem statement that we can use quantum computing. So to sum up, quantum computers are fundamentally different form of computing. So whatever you have, GPU, CPU, good. They do all sort of stuff. But QPU, quantum processing unit, that's what will come in. Let's say 5 to 10 years. That'll be built on qubits, not on bits. It will be fundamentally different. It is nothing. You can't say it's a more powerful supercomputer. That's a bad analogy to keep. It is a fundamentally different form of computer, and it does exponentially faster, and it is computationally cheaper and can do solve hardest problems for human. So there are a lot of sectors. There is a lot of sectors. There is a lot of use cases that we have identified right now. So it starts from agriculture, financial service, healthcare. I can't go on most of them, but I'll try to give you one example. Let's take example of logistics optimization. Very simply, you have an Amazon delivery guy coming to, let's say he has to deliver to 20 homes a day. He has to deliver to 20 homes, and think about how complex that route would be. Let's say he has his warehouse and he has 20 homes in 20 different part of that particular city, and think about how many combination of route there will be to cover all the 20 maps. For example, he can cover house number 1, house number 2, house number 3, to house number 20, or he can cover house number 2, house number 19, house number 18. There are a lot of these paths that can happen. So from all these possibilities, from all this combination, you need to find the less, path which has the least cost associated with it, that is fuel cost, then that is energy efficient, that is least distance. So this sort of optimization problems, that is very hard. Then there is problem statement in machine learning, which has very difficult in terms of pattern recognition. So one example, our previous speaker talked about Ekta, was fraud detection. It's very difficult to find the pattern of the fraud happening. So when we say fraud happening, I'll give an example there. In a data set of 2 lakh data points, only 100 of data points will be fraudulent. Only 100 of them will be fraudulent. How are you going to find that minute pattern of finding that fraud? So that sort of problem statement will be suitable for quantum computing. So there are a lot of this sector, there are a lot of use cases that we have identified right now to look at quantum computing. Now, coming to what is the current state of quantum hardware, that is QPUs right now. I'll give you what state is right now. They're still in experimental phase. Quantum computers right now are still in experimental and exploratory phase. You can't use them to build anything in production. So I won't hype it up. This is the situation right now. You can't use it to build anything in production like generative AI, but there is huge potential. That's why you need to be prepared for that. You need to have this in your horizon to make sure that you're being prepared for that. Now, you must be asking, okay, you've told about quantum computers, where are they? Where are they, right? So the best part is you can actually access these quantum computers or QPUs via cloud right now. You can go to Amazon Web Service, that is AWS. AWS has a separate cloud platform called Bracket, B-R-I-K-E-T, Amazon Bracket, where you will get access to quantum computers of Rigetti, IonQ, Oki. So you might not find familiar names. These are quantum computing startups. These are actually quantum computing startups that are coming up. These are not. We also have quantum computers from IBM. They have that's in IBM Cloud. You can use that. Then we have in Google Cloud. Google has built quantum computer. How many of you heard about Willow? Google's Willow, right? Yeah, that created actually a huge sort of mainstream news about quantum computers. So they are also still in experimentation phase. They're building that computer. They have not put the computer in cloud till this point. Google haven't yet put the computer for us to experiment or for us to look at. Then these are the cloud providers and the quantum computers that you can access right now. Now, coming to, so now first I talked about quantum computing hardware. Now, how do you write? Like, how do you actually write something on it, right? How do you try to write something? How do you try to experiment with it? You have your quantum computers in the cloud. But how do you actually write quantum computing program? So the best part is that we have Python SDKs, which is available right now, open source, free, which you can use. There is a small learning curve for it. It takes some time. It's because um, the program that we write in quantum computers are still in gate level. So when I say gate level, how many of you remember you studying electronics when you're graduate and you putting up gates for each bits, AND gate, OR gate, NAND gate, keep on adding all these gates, right? And then you build a circuit, then you get an output. So you put 0 in, you get 1 out. So now you get 0 in for NAND, AND gate, you'll get, so NOT gate, you'll get 1 out. So this sort of level, that is where quantum computers are still in. So you would be sitting and writing actually the circuits. You'll be saying, okay, you have instead of bit, we have qubit. Take first qubit. I'll add instead of this gates, NAND gate, OR gates, we have H gate, X gate, Y gate, Z gate. Again, a little bit of learning curve there. You need to understand how this actually works. So you add a gate, H gate, you add X gate, then you build a circuit, then you add some other things at the end of it, then you actually make an algorithm. And this SDKs actually help you to build that algorithms. So Qiskit is from IBM. Then we have Pennylane. It's from another quantum computing startup called Xanadu. Then we have Amazon Bracket. Then we have Circ, which is from Google. So, as I've talked about the software, I've talked about the hardware, I've talked about this quantum Python services as well. Now let us start talking about quantum algorithms. So here I'll try to spend more time, try to go through all of them. I'll try to give ideas on what we have done, what you can do, and what are the use cases that you can probably look at afterwards as well. So let's start with machine learning because of course it's an ML conference, quantum machine learning. So in quantum machine learning, you can essentially think of it as what we'll take the machine learning framework, the framework what you already have. You try to take it and you try to find a part of it which probably will be computationally harder or computationally time taking for your systems, GPUs or CPUs, and then you try to give that to our QPU. That's essentially what we do. You essentially will have a hybrid approach. So you'll have a QPU which will be doing some part of it. You'll have a CPU or a GPU which will be doing another part of it. So when I talk about quantum machine learning, first one, the most widely used will be quantum support vector classifier. So you all would have heard about SVC, right? SVM, SVC, support vector machines, support vector classifiers. So we have a quantum version of it. So the quantum version of it, you might remember we have a kernel. There are multiple types of kernels, I'm not a ML expert, RBF kernel, linear kernel, quadratic kernel, and all of that. Instead of this classical kernels, what we'll have a quantum kernel. So kernels are essentially matrix calculation, right? So they're trying to do the matrix multiplication, try to get that value output. So instead of using that, once you use a quantum kernel, the inherent physics will take care of it, and you'll be able to speed that process up. You'll not be able to do all that matrix manipulation and take more time. And that only part will be done by quantum support vector classifier. And then we have an improved version of this called automatic quantum support vector classifier. So it's instead of you finding the kernel, it will actually try to find the kernel for you. Then there is kernel training. So instead of kernel being a static one, you'll have a variable kernel which can be trained so that it'll be able to learn through the process and improve itself. Then we have quantum random forest. It's a very, very new uh, new algorithm that have been come up. Very few works have been done on it. So they have tried to take the try to take random forest and have tried to build quantum random forest. The decision trees in the random forest will be QSVM instead of your regular SVM. So that's how it differs. And then we have quantum reinforcement learning. It's a very interesting algorithm, quantum reinforcement learning. So there also, that agent we will be using quantum neural network. Okay, I've missed quantum neural network. Probably I'll talk about quantum neural network. So we have quantum neural network. Quantum neural network, what happens is that you have neurons in your normal machine learning. Instead of neurons, what we'll have is parameterized quantum circuit. So I talked about circuit. There will be circuits which can be trained. Instead of neurons, we'll have the circuits which can be trained. So again, this will help us to improve the hopefully the computational efficiency, using less power, and also trying to fasten up this process. And using that, we'll have quantum reinforcement learning. Again, the agent will be a quantum neural network. I'll be very similar to reinforcement learning. We have actually done brilliant work with that. So one good example that I will try to put up here is we have actually used QRL, quantum reinforcement learning, in a challenge which was conducted by Amazon Web Service, AWS, which actually where we actually try to use QRL and compare it to classical reinforcement learning, the normal reinforcement learning. What we were able to find out is QRL uses 1 by 120th parameters, or the 1 by 120th parameters compared to reinforcement learning. The parameters that is associated with the neural network, instead of 800 parameter, we were able to come around 60 or 80 parameters in QRL. So that itself shows how much computationally you can reduce the expensiveness of these neural network architectures. And then we have QGANs, quantum generative adversarial networks. So QGANs essentially, hopefully we all know GANs. They were the OG generative models even before LLMs came, right? They were the ones which we used to generate all those images, cat images and everything. But now nobody uses that. But still they have use case in different areas. In generative adversarial network, we have two machine learning models. One is the generator and one is a differentiator. What we'll do in QGANs, we'll take differentiator as the neural network itself, and generator will be our quantum neural network. So essentially, again, all of this will be hybrid ones. And then quantum reservoir computing, which is a very, very nascent field and a very exciting field. How many of you work with reservoir computing, classical reservoir computing? Okay, nobody. So it's a lovely field that I love to read more and to understand more. So reservoir computing is essentially where you have a data set and you need to, instead of giving it to a neural network, you actually parse it to a physical dynamical system, so that encodes a data set and tries to uh, you know find out the patterns inside that. So this will actually help you to reduce the neural network complexity, again computation that we need to do that. For example, one of the physical unit that they use would be like a robotic arm. So they'll try to feed this data into a the dynamics of a robotic arm, and they'll after that they'll take the output and then they'll do simple machine learning like SVMs or linear regression to find out the classification. So this reservoir computing try to take away neural networks and put in some dynamical systems instead of neural networks. Now there is no other random dynamical systems than quantum systems. These are essentially the best system where you can have randomness, and that is why quantum reservoir computing will help in building that. So this covers all of the machine learning algorithms in quantum computing right now. So these are the only quantum machine learning algorithms that is out there right now, which you can start looking at. So all of this can be used for any of the machine learning use cases. You can always try to look at this and try to compare it with your machine learning models and see if it is, where the performance are. But again, the only problem is you won't be able to use like a huge number of data points. At max, you'll be able to use 2,000 data points because the systems that we have very feeble, very small scale systems. They can only handle that much. Then we come to optimization. So the optimization problem statement is where I've talked about before. You have like a logistics route optimization where you have lot of possibilities and you need to find the best optimal output from that possibilities from that particular solution set. Hope you're okay. And that part that will be disrupted first. That optimization problem statement, optimization industry will be disrupted first by quantum computing because we are seeing good improvement right away. So we usually use three different techniques for that. But one is called variational quantum eigensolver. Then there is quantum approximate optimization algorithm. Then there is quantum annealing. Again, I can't go into much depth of it, which is very quantum physics in nature. So if you want to discuss, I'll be happy to talk about all of these three algorithms afterwards. So this essentially trying to set up something or sort of quantum systems and trying to mimic how do we optimization. And quantum annealing has actually proven a good technique for a lot of optimization problem statements. So this is going to be disrupted soon. Then there is quantum simulations, which will be your you have a system. You have a system probably like, for example, um, digital twins. You need to simulate how somebody's health would be going from one point to another according to different parameters, or you want to simulate, let's say, a game simulation, or you want to simulate chemistry, which is a fundamental starting point of where it had all started. Um, it was actually started by Richard Feynman. How many of you know Feynman? All of you know. So Feynman actually said while he was trying to get chemistry simulation of a molecule, he was saying, "Damn it, nature is not classical. Nature is not built by using voltages and bits. It is quantum, and we need a quantum computer to understand it." Actually, that is where it all started. So chemistry simulations. So for example, you need to find better battery. You need to go beyond lithium ion. What will be the next one or two materials that you can use? You need to simulate better materials for different sort of use cases. What will be that? You need to find drugs, better drugs. So even AlphaFold has done all those great work. Protein folding may have done great work, but still the problem is it can't explain, right? It can't explain how it predicts. It just predicts because of the data set. But if you really need to understand how it does, you really need a quantum computer to actually do all those mathematics behind it and give you that reaction and output afterwards. That way, quantum simulation is actually going to be much bigger part of it. So what I've tried to put up here is a lot of information I know. So there is quantum computers out there which using different SDKs, Python SDKs, Python libraries, you can write these algorithms for use cases that I've shown here. So that is the common theme. I know there is huge amount of information. Each of these slides would be one different session itself. So in that theme, I would love to again shamelessly plug my product here. How we would be, helping you to better use or better write quantum algorithms. Now, because there are a lot of this algorithm, there is a lot of this Python SDKs. Then there is different QPUs. How do you actually start writing, right? So if you can play the video, that'll be great. This is the demo of our product. It'll be released very soon. Hopefully, I think this is the first place I'm actually publicly putting out my product. So thanks a lot for being a wonderful audience. If you can play the video. Um, can you call and video? So the idea of Bloq is essentially you can use Bloq Quantum platform to start writing quantum algorithm without actually understanding the complexities. It is a low code platform which actually helps you to, yeah.
Hello everyone, welcome to Bloq Product Demo. Our platform makes it much more easier for you to write quantum algorithms. So, how does it work? So, for people who are beginners and just starting to know how to write quantum algorithms and just want to test them out, they can come to this module, which is the experiments module. Let's say we have a use case like credit card fraud, and we have a data set. You can upload one as well, and then you can go to advanced options, select the features that you want and select the size of the data set. You can select the train and test split. Done. You can select the algorithm you want to run, select the
So you could see
parameters like number
QSVM
of
that I've just talked about.
qubits, feature map, and the simulator that you
These
want
are
to run it with.
basically inputs that
Just
goes to
hit on run,
QSVM. So you can just
and
simply play around with and
just like that
you would
the
have got.
algorithm has been queued and it will complete its run very fast. Now once it is completed,
So you will
you
be
can
able to see
see
the
it will
results
look like
also,
this.
like
When you
accuracy,
click on
precision,
this,
recall
you
in the
get
left hand.
the
Yeah.
accuracy score, F1 score, precision, recall, and you can also click on this button to generate a code for it, where I'll show you in a bit. So this is now completed. You click on this, you can see these are the results. Now you click on this button and in a second the file will be generated. You click on that, and now this is for someone who actually knows how to write quantum algorithms and want to
So
experiment more
using
with
this,
the
you will be
actual
able to
code.
actually
So you have the code right
include your
here,
workflow here, like
and this
your
will make it
classical
much more
workflow, other
easier for
workflow to
you to
this
now
part.
just make changes and uh, just just write it by yourself. But let's say if you want to write more different quantum circuits and try out many variations of it, so we make that as well much more easier just by going to the circuit builder
This
module.
is where I say
So let's
circuit,
create a
right? This
new
is how we
circuit
build a
right
circuit.
here. Just like that,
You
you
actually need
have
to
an
build
empty
all the
circuit here.
circuit. You need to actually write
Now
all those circuit, which
you
is very,
can
very
drag and
difficult.
drop any quantum operations that you want. We support a lot of operations. We also support parameterized operations as well. I'll show you in a bit. So this is how you can just create a circuit. You can also visualize the probabilities as well. Then we also have rotations gate, which you can actually edit the rotations and just like that. And yeah, you are done. And you can also copy this code. This is the OpenQuasm code. You can go back to the editor and then use Qiskit to read the OpenQuasm code into an actual quantum circuit. And yeah, this is done. You can easily create quantum circuits with this. I hope you found it very useful. Thank you. Hello everyone, welcome to Bloq
Oh,
Product Demo. Our
so essentially, anybody who's sitting here can actually start writing quantum algorithms using our platform. So we'll be actually supplementing whatever you'll be writing with really good documentation, which you can easily, it'll be fun to read and easy to understand. So the first part you probably would have understood. Okay, the experiment tab simply give some input, put your data set, can find the results, well and good. Second part is where you can actually get the code. You can probably write your own code, add your classical processing, data pre-processing, post-processing, a lot of things you can do. And then this, once you have become a little more experienced, right? There are parts where you can actually build your own circuits to better map the data that you have. That is one very important part, and that is where the circuit builder, the third part, so he's my co-founder, CTO, Jay Patel, such a brilliant guy. So great kudos for him as well. So that's where the third part, the circuit builder, comes in handy. Because think about it, if you need to have, if you have like 100 qubit, how are you going to write gates connecting to all those qubits sitting down? It's taking a lot of time. So with that, you'll be simply able to visually build a circuit and take the code, put it in the platform, again run it, and actually build your own use cases for any of your use cases that I've showed. So yeah, with that, thank you. Thanks a lot for being a wonderful audience. I'll be happy to take questions.
Thank you, Srikutan. Does anyone have questions?
If you can go back to the slide. You can scan this code. Hopefully the code, or else you can go to bloq.in and book a demo if you want to know more about the product.
Hi, Shrikota.
Hi.
Nice talk. I won't put you on the spot. You know, Jensen Huang from NVIDIA recently at CES said
Yeah.
quantum computing, decent quantum computing is at least 15 to
15
20
to
years
20 years
away.
Yes.
And you've got a product, you've raised up to 1 crore of funds, and you got something which is working. So what am I missing?
So Jensen Huang said 15 to 20 years. Bill Gates said 3 to 5 years. Google said 6 years. So nobody knows the answer. So, so the thing is that with quantum computing, nobody expected DeepSeek, right? So nobody will and what I'm saying is the timeline, it can vary. It can be 15 years, it can be 3 years, it can be 6 years. So what I'm saying will be 6 years because the Willow team that have done that excellent work, they said 6 years. So I think that's what I'm going with. Now, what you're missing is basically at this point of time, there are around 400 plus enterprise users, including HSBC, JP Morgan, Tata Mahindra, like BMW, Airbus, all of there. They want to get into quantum computing right now because they know the potential that they're going to lose out. It's huge. It's unimaginable for them, and they want to start right now. And they are starting to experiment and implement. And this tool will be for them to start experimenting much more faster and easier. So that's what we are starting with. And once it is fully fledged, once it's mainstream, that's when we'll evolve our platform to actually help them to deploy the solution. So that's actually the bigger plan that we have.
Thank you.
Yeah.
Hello, I'm Amit.
Hi, Amit.
So you had said that in QNN, quantum neural network, instead of neurons, we use circuits, which can be trained.
Yeah.
So I thought that circuits are deterministic. So how a circuit could be trained?
So when I say train, there are gates called rotational gates. He would have probably shown that. You would have seen it there, rotation gates. So rotation gates have a theta or an angle associated with that gate, right? That instead of making that deterministic, that particular angle, let's say pi by 2 or at 180 degree, you can say just theta. It's a parameter, and then you try to tune it that to your data set or whatever you try to model. So that's how make it parameterized.
And then I wanted to know that what is the reason behind that limitation of 2000 data point that you have said?
It's because right now the quantum computers, the maximum qubit count. When I say qubit count, you compare the device that you have will have trillions of bits, more than that, right? Trillions of bits. You're competing that to just 100 qubits, and that too they're not they're not good enough to perform these operations. So this 100 qubits can only handle this much amount of data points. So that's a limitation.
By when do you think that this could be overcome?
So again, that's the problem, right? Jensen Huang says 15 years, Google says 6 years, Bill Gates says 3 years, so I'm hoping 6 years. So
okay.
Yeah.
Thank you.
All of machine learning which we have today is based on matrix manipulation.
Yeah.
So why don't you offer matrix manipulation as a fundamental block which can be used?
Yeah, lovely, right? So there is an algorithm called HHL algorithm which actually does that. So I'll be happy. Yeah, we can hopefully get that into our system as well. Yeah, thanks a lot for that. Any more questions? I think we all want to run to the stand-up comedy, right?
I think, any other questions? No. Yeah. Thank you so much, Srikutan.